Okay, let's start the new problem. So this is the layout for which we have to design the shaft. So figure shows a shaft which are supported between the two bearings C and the D. These are the two bearings C and the D. The length of the shaft between the bearing is equal to 1000 mm, on which the pulley A and the B, both the pulleys are of same diameter. Diameter of the pulley D is equal to 500 mm. Both the pulleys are mounted on a shaft. So at 200 mm from the bearing C, and the pulley B mounted again 200 mm distance from the bearing D. So this is the arrangement. Again from that this both the pulleys, direction of that this power. So pulley A transmit the power in a vertical direction. So that belt tension shows the pulley A transmit the power in vertical direction, and pulley B transmit the power in horizontal direction. So this side view shows that pulley B transmit the power in a horizontal direction and pulley A transmit the power in a vertical direction. In addition to that, we have the given data. The ratio of belt tension, that is given T1 upon T2 is equal to 2.2. Okay, this is another data we have. Another data we have, the maximum belt tension in a pulley. So that is a maximum belt tension, that is a T1 is given, which is equal to 2500 Newton. In addition to that, so it is given that shaft is made up with plain carbon steel with SUT. Shaft is made up with the plain carbon steel with SUT 800 Newton per mm square, and SYT is equal to 550 Newton per mm square. In addition to that, we have to design the given shaft according to ASME code. According to ASME code design, so we have to design the shaft, and for which the combined shock and fatigue factor in bending and twisting is given as KB is equal to 1.5 and KT is equal to 1. So these are the two factors called as combined shock and fatigue factor in bending, and this one is the combined shock and fatigue factor in twisting, so is given. So this is the required given data for this arrangement, for which we have to design the shaft according to the ASME code. Now let's the solution of this problem. Okay, we'll start the solution of this problem. The first step according to ASME code. According to ASME code, the first step is to calculate the tau permissible. So here we have to calculate the tau permissible. According to the guideline, tau permissible is equal to 0.3 SYT or 0.18 SUT. We have both the values, 0.3 into 550 SYT or 0.18 800 SUT. Calculate both the values. It comes, one is a 165 Newton per mm square and another is 144 Newton per mm square. So here whatever two values we calculated, from which we have to select the minimum value, that will be the tau permissible. Now selecting the minimum value, tau permissible is equal to 144 Newton per mm square. So this is the minimum value of tau permissible from the first step according to the ASME code, and from which we have tau permissible is equal to 144 Newton per mm square. Now two pulleys are mounted on a shaft, and we know for transmission shaft pulleys are keyed to the shaft. Therefore there is need to consider the effect of the keyway. So you write here, consider the effect of keyway. And as we know, if the keyway are cut on a shaft, it weakens at that location because the failure may possible due to stress concentration. And according to ASME code, if keyway are present, the above tau permissible value is reduced by 25%. That means multiply it by 0.75 into 1444. So that comes 108 Newton per mm square. So this is the final value of the tau permissible we have to select for the further calculation of the diameter of the shaft. So that tau permissible is equal to 108 Newton per mm square is the permissible shear stress that we have to use to calculate the diameter of the shaft. Now moving towards the next step for this problem, we have to calculate the value of the torque. We know the belt tension is given in this problem. We don't have the value of the belt tension because here power transmitted through the belt drive. So we have the formula T is equal to T1 minus T2 into R. This T1 and T2 are the belt tension in a tight and loose side, or maximum belt tension and minimum belt tension, whereas this capital R is the radius of this pulley. So right now we don't have the value of the T2. T1 is known, that is the maximum belt tension that is given in a problem. We have to calculate the capital T because we have to calculate the torque from this equation. We have the value of the R, both the pulleys are of the same diameter, and that is equal to the 500 mm. So now moving toward the T1 and the T2 calculation, we have T1 by T2 is equal to the 2.5, sorry not 2.5, 2.2, and here it is given T1 is equal to 2500 Newton. So if T1 is known, ratio of belt tension is there, therefore we substitute the value of the T1 in this equation and T2 can be calculated. So here T2 is equal to 1136.36 Newton. So now we have both the T1 and T2. We have the value of the R. T1 is known, T2 is known. Substitute in this formula both the T1 and the T2 and calculate the value of the torque. So that torque will require, so that we have to substitute the final equation according to the ASME code. After substituting both the values of T1 and the T2 and the radius of the pulley, we have torque is equal to the 340,909.09 Newton mm. So this is the value of the torque we have. So that is our answer number 2. where we calculated the torque. And by using the belt tension ratio, by knowing the value of this radius of the pulley, by using the formula for the belt torque, so we obtain our answer number 2, that is the torque is equal to the 340909.09 Newton mm. Now next step, we have to calculate the maximum bending moment. So for that, so we have to draw the vertical and horizontal loading diagram. As in this problem, both the pulleys, pulley A transmit the power in a vertical direction and pulley B transmit the power in a horizontal direction. Therefore, there is need to draw both vertical and horizontal loading diagram. So I'll start here to draw the free body diagram. So this is the total length of the shaft. So this is the position of the bearing C. Okay. I will start to draw the horizontal loading diagram. Okay. So this is the location C. This is the D. As the given diagram is horizontal loading diagram, therefore we can say RCH. This one is the RDH. These are the locations of the pulley, and from the first figure we have pulley B transmit the power in horizontal direction. So only consider the pulley B here, and the net downward force for the pulley B is the summation of T1 plus T2. So we have the distances. So we know this distance is equal to the 200. So here this is the location B. This is the location A. At A, no transmission of the power in horizontal plane by the pulley A. By pulley B, power is transmitted in horizontal direction. So that only we consider in a horizontal loading diagram. So this distance 600 and remaining is the 200. So this is the free body diagram. This is the free body diagram in horizontal plane. Now for which the next step is to calculate the bearing reactions. So we can write RCH plus RDH is equal to T1 plus T2. So make the summation of T1 plus T2. Make the summation of T1 plus T2, and we have summation of the T1 plus T2 3636.36. If you make the summation of the T1 and the T2, that equals to this one. So we name this as equation number 1. Taking the moment about the C, we have this 3636.36 into this distance 600 plus 200 clockwise, that's why it is a positive 800. Okay. Now again this RDH, it is in anti-clockwise direction, so minus RDH into this total distance, entire distance about the C 1000 is equal to 0. So from here we will get the value of the RDH, that is equal to the 2909.09 Newton, and that of substituting the value in equation number 1, RCH is equal to 727.277 Newton. Is it clear? So here we have the value of bearing reaction. Now moving toward the bending moment. These are the four locations where we have to calculate the bending moment. And bending moment at C, bending moment at A, bending moment at B, and bending moment at D we have to calculate. And we'll start with the bending moment calculation. So here, so now we start the bending moment calculation. We write bending moment at C is called as a MCH, as it is a bearing support, so it becomes 0. Then bending moment at A is called as a MAH, is equal to this RCH into 200. We have the RCH 727.277 into 200. That is the bending moment at H. So that equals to 1454 Newton mm. Similarly, bending moment at B is equal to, which is denoted by MBH, at this location, RCH into 800, RCH into 600 plus 200 at this location. This is in clockwise direction. So by calculating this one, we have the value 581818.16 Newton mm. And last, bending moment at D, MDH is equal to the 0 bearing reaction. So we can draw the bending moment diagram. So by plotting here, we can also plot the bending moment diagram. See here. So at this location, bending moment is 0, C and D, which are the bearing reactions. At location A and at location B, we have the value at location A 1454. So suppose we mark here approximately that distance. And this bending moment at B, so it is quite higher than this one. So we'll mark at this position. So this is the bending moment. Both are positive. So the positive bending moment diagram. So we have, so this is the bending moment diagram for this one. So here, so this complete the calculation of the first part of that of this bending moment. So for the horizontal loading diagram, so we done this calculation where we calculated the bending moment at A and bending moment at B. This problem also needs to calculate bending moment in a vertical direction, because pulley A transmit the power in a vertical direction. Therefore, in next step, we'll see the free body diagram for the vertical loading, and then we'll go for the design calculation. Now we'll see the vertical loading diagram. Again the same free body diagram. As from the first figure, pulley A transmit the power in a vertical direction. So at location A, the sum of T1 and the T2 is a net vertical downward force. At location B, pulley B transmit the power only in horizontal plane, so no that load at the location B in a vertical plane. So vertical loading diagram, so this is the point RCV, V stands for vertical, RDV, V again stands for vertical, and these are the distances. This is the vertical loading diagram. This diagram is called as a vertical loading diagram. Again, we have to repeat the same procedure to calculate the bearing reactions RCV and RDV. Again, we write here RCV plus RDV is equal to summation of this T1 and the T2 3636.36, we can name this as equation number 1. So name this as equation number 1. So thereafter so we have calculate the bearing reactions at this location, and these are the points. About this location C, we can calculate the bearing reaction. So about the point C, we can calculate the bearing reaction. So take the moment about the C. So we have moment about the C. So we have 3636.36 into 200. Okay, about this one, this into this 200. Okay, then this is again anti-clockwise direction, minus RdV into 1000 is equal to 0. With this, we have first bearing reaction RdV is equal to 727.27 Newton, and that of RCV is equal to 2909.09 Newton. We have the bearing reactions for this vertical loading diagram, and our aim behind this is to calculate the bending moment at these 4 locations. Again, we repeat the same procedure to calculate the bending moment at different locations. So here again we write bending moment at C is denoted by MCV. Again it is a 0. Next, bending moment at A is MAV is equal to RCV, that means 2909.09 into 200. It is in clockwise direction, so it becomes, after calculating it, 5818.18 Newton mm. Okay. Similarly, bending moment at B is denoted by MBV, and this MBV at B, RCV into 800. See here, RCV into 800. Okay, minus, this is anti-clockwise direction. As this is a clockwise direction about the B, therefore it is a positive sign convention, RCV into 800, and minus this T1 and T1 plus T2, it is in anti-clockwise direction with respect to B. Therefore, this summation of T1 and T2, that is 3636.36 into 600, that is minus because of anti-clockwise direction. So we have, after doing the calculation, we have 1454.56 Newton mm. This is a bending moment at B at this location, and last bending moment at D, MDV is equal to 0. So this calculate the bending moment at different location, and that of we can draw the bending moment diagram. See here, this is a C, this is a D point, this one is a A point, and this one is a B point. As both the bending moment calculated, it is a positive. Bending moment calculated, it is a positive. So we'll draw here bending moment with respect to the magnitude of the bending moment at the location A and B. So both, this is again the positive bending moment diagram. So this is the bending moment diagram in vertical plane. Now The main aim behind this homework to draw the vertical loading diagram, to draw the horizontal loading diagram, thereafter to calculate the bending moment in a horizontal plane, calculate the bending moment in a vertical plane, is to calculate the net bending moment at the respective point. So that we have to calculate the maximum bending moment, and we are interested to calculate the maximum value of bending moment. So now we have to go for the net bending moment at respective points. See here, bending moment at C is equal to mch square plus mcv square, as it is a 0, so it becomes a 0. Bending moment at A is equal to, again the formula, mah square plus mav square, and that is equal to, by substituting the value of both the bending moment in horizontal and vertical plane, we have 599,724.45 Newton mm. Similarly, bending moment at B, we have mbh square plus mbv square, and that is equal to, again it comes 599,724.45 Newton mm. And bending moment at D, again it is a 0. After calculating the net bending moment at the respective points, so fortunately here at both the locations A and the B, we have the same value of the bending moment, because the same diameter of the pulley at the same distances. But when for any other problem, whatever bending moment you calculated for all these points, from this bending moment calculation, select the maximum value, that will be the value of the m. Here both values are same, so m is equal to 599,724.45 Newton mm. This is our answer number 3 to calculate the value of maximum bending moment. Now we have to use the final formula to get the last answer. Tau permissible is equal to 16 upon pi d cube, in bracket kb m square plus kt t square, bracket complete. In this formula we have tau permissible is equal to 108, which is equal to 16 upon pi d cube, in bracket value of kb and the kt are known to us. Kb is equal to the 1.5, value of m is known, 599,724.45, so that whole bracket square, plus kt Kt is equal to 1 into T, torque already we have 340,909.09 bracket square. This hold under the root. After simplification, the unknown is the D. After simplification, doing the calculation carefully, finally we will get the answer D, and that D calculated by using this final equation is equal to 35.65 mm. This is the final answer, that D is equal to 35.65 mm, and that we round up to the next integer value. So D is equal to 36 mm. So here this is our final answer for this problem. D is equal to 36 mm.